Hello students, hope you're doing well. Today let's take a look together at the topic of thermal equilibrium in the 9th grade. First, we'll go through the specific steps to solve this problem, and then I'll summarize the relevant content for everyone, okay? If you haven't tried this problem yet, please pause the video now, try to solve it yourself based on the question, and write your answer in the comments section. After that, listen to my explanation and see if your answer matches, alright? There are two containers, A and B, each filled with equal masses of water. The water temperatures are 25 degrees Celsius and 75 degrees Celsius, respectively. First, a metal ball at 65 degrees Celsius is placed into container A. After reaching thermal equilibrium, the water temperature in container A rises to 45 degrees Celsius. Then, the metal ball is quickly taken out and placed into container B. After reaching thermal equilibrium, what will be the water temperature in container B? In this scenario, it is stated that heat loss is neglected. When heat loss is neglected, you should note that the amount of heat released by the hot object is equal to the amount of heat absorbed by the cold object. Therefore, based on the fact that heat loss is neglected, we can directly set up an equation. QC equals, is it okay to call it Q released? Next, for the detailed breakdown process, we need to analyze it ourselves. Since there is quite a bit of content for the main point here, I'll first explain it to everyone using a diagram. So in this case, we have two containers, A and B. Both containers are similar and each contains an equal mass of water. Alright, so for container A, the temperature is 25 degrees Celsius, while for container B, it's 75 degrees Celsius. Now we have a metal ball at 65 degrees Celsius, a ball at 65 degrees Celsius. This ball is placed into container A. After reaching thermal equilibrium, the water temperature rises to 45 degrees Celsius. So let's first take a look at container A. After it reaches thermal equilibrium, our entire analysis, or rather the whole process of thermal equilibrium, still needs to be represented with a diagram. Now, let's draw a line at the higher position to represent the higher temperature. At this point, the metal ball at 65 degrees Celsius is placed into the water at 25 degrees Celsius, so the object with the higher temperature should be the ball. Its initial temperature is 65 degrees Celsius, and the object with the lower temperature should be the water. Its temperature should be this one, 25 degrees. Then, after reaching equilibrium, after the heat exchange, the final temperature will tend toward the same equilibrium temperature, which is given to us as 45 degrees Celsius. The equilibrium temperature is 45 degrees Celsius. The temperature drop, delta T1, is 65 degrees Celsius minus 45 degrees Celsius, which equals 20 degrees Celsius. And then the temperature increase of the water in container A can also be expressed from 25 to 45 degrees Celsius. So the temperature increase for the water, T2, should also be 20 degrees. Can everyone see that? Based on this diagram, if we analyze it, we'll find that delta T1 is also equal to T2. Now, let's set up our equation. I'll write it out in full first. I say Q absorbed equals Q released. QC is the cold C, which refers to our water system. In this case, it should be the water in our container at home. So the water at home is multiplied by the mass of the water at home and then multiplied by our delta T. For water, it should be delta T2, which at this point is equal to our... If we need to find C, then I'll use C to solve it. Then M9 is multiplied by the temperature change we're looking for, which is delta T. In this equation, it's not hard to see that since these two are the same, we can get that seawater times M water equals C ball. M ball. Alright, at this point, this corresponds to the false one. It's the false one. Okay, after we've got that, let's look at the second part. It says that after reaching thermal equilibrium, the ball inside here should have a temperature of 45 degrees Celsius. Then, this ball at 45 degrees Celsius is thrown into our container, for another round of thermal equilibrium. And we're asked what the final equilibrium temperature is. So at this point, our ball should be put into our container. Let's take a look. So when it enters our container, it's the same process. At this point, the one with the higher temperature should be the water. It's at 75 degrees Celsius. And the one with the lower temperature now is our ball. Its temperature is 45 degrees Celsius, and we're being asked what the final equilibrium temperature will be. Let me use a prime symbol to represent it, okay? Let's take a look. At this point, the temperature of our ball will increase, and the temperature of the water in our container will decrease. The decrease in the water's temperature I'll denote as delta T3. To find the increase in temperature, I'll use delta T4 to represent it. Similarly, when you don't have any ideas, when you have no clue about thermal equilibrium, you should first write out the equation. The only formula you can really use here is the thermal equilibrium equation. Once you write it out, it'll be easier to figure out your approach. So similarly, Q7 equals Q2, and we can write that out. This term should be C times the mass of the water. We won't distinguish between the two here, since the specific heat capacity of water is the same, and the mass of water in both containers is also the same. So it's also C times the mass of water. Then delta T3 should be related to our C ball, mass of the ball, and delta T4. All right, everyone, take a look. According to the derivation we just did, our C water times mass of water should be equal to our C ball times mass of ball. So doesn't that mean these terms can be cancelled out? So as expected, our delta T3 is equal to our delta T4. If we break down this equation, it's our 70 and 50 degrees. So if we subtract our first term with a prime, it should be equal to our first term with a prime, and then subtract 45 from this equation, there should only be one unknown left, right? That is, the second term equals 120. So what is this term equal to? It's 60 something. So in the end, we solve and get that our answer is 60 something. Everyone choose 2B. For the simplest thermal equilibrium problems, you should be able to set up just one equation and solve it. If it's a bit more complicated, then you'll need to set up two equations. Sometimes it might even be 3 or 4 equations, but that's okay because our equations provide a unique way to represent the problem. Just write it out a few more times and you'll always find the corresponding relationship, right? So, to sum up this type of problem, the first thing we should do is draw a diagram. Yeah, just draw a diagram like mine with 3 lines. The second step is to clearly label our subscripts. There are multiple states and multiple conditions, so make sure to clearly label the subscripts. Don't get yourself confused. If you can do these 2 things, I believe that students watching this video definitely won't have any problems with this type of question, right? All right, that's all for this problem. If you found Mr. Wang's explanation helpful, remember to give him a like. Bye-bye.